Course CH442 Surface Chemistry, Catalysis and Colloids. Part 1 Liquid Gas and Liquid Interface. Part 1 Liquid Gas and Liquid Interface. Course Outlines. CHE442 Intended Learning Objectives. The understanding and appreciate the influence of surface and interfacial tension in everyday life, in detergency, contact angle, and or flotation, and capillarity in nappies and blotting paper. Students should learn the various methods of measuring surface tension and their limitations. In the gas-solid interface, we hope to achieve a clear understanding of chemisorption and physisorption and how they are applied in heterogeneous catalysis. They should be able to use Langmuir and BET theories to determine surface area of solids from adsorption data. They should have an understanding of the colloid state, prepare and purify colloids and nanoparticles, characterize them, and the causes of stability and instability of colloids. Course outlines: elementary surface chemistry and colloid science, liquid gas and liquid interface, interfacial and surface tension, curved interfaces, drops, bubbles and menisci, adsorption and orientation at interfaces, monomolecular surface films, thermodynamics of adsorption, Gibbs adsorption equation, adhesion, cohesion and spreading. Solid liquid interfaces, contact angle and wetting, detergency or flotation, adsorption from solution. The gas-solid interface, adsorption, physisorption, chemisorption, Langmuir's model, Friendly and Temkin models, adsorption isotherms, the BDDT classification, the BET model, surface area determination, thermodynamics of adsorption, isosteric heats of adsorption, surface catalyzed reaction kinetics, and preparation, purification, and properties of colloids and nanoparticles. Preparations: dispersion methods and condensation or nucleation methods. Purification: ultrafiltration, dialysis, electrodialysis. Characterization of nanoparticles. Particle sizing and relative molecular masses. Double layer theory. DLVO theory of colloid stability, effect of salt, charge of ion, Haddis-Carl's rule. Recommended textbook for this course are Introduction to Colloid and Surface Chemistry by Duncan J. Shaw. Right, let's get to the nitty-gritty. Let's start with kinetic theory. Intermolecular forces exist between particles. States of matter are a manifestation of the magnitude of these forces. If you look at the diagram given, molecule A in the middle of the liquid has forces surrounding it up, down, and sideways. However, molecule B at the interface has forces into the liquid along the surface, but no forces upwards. So at the surface, molecules experience imbalance of these forces. Hence, molecules tend to be dragged inwards. Thus, the surface tends to contract, i.e., the surface is under tension. Consequently, 1. Drops tend to be spherical. 2. Bubbles tend to acquire spherical shape too. Let us look at surface tension. Let us ask ourselves the question, what is surface tension? For a liquid, this is the force acting at right angles to a line of unit length on the liquid surface. It is measured in millinewtons per meter. Sometimes it is better to define surface tension as the work required to increase the area of the surface isothermally and reversibly by unit amount. Looking at the diagram with a breadth of L, if we change the length by dx, the work done is equal to the force gamma, the length L, and the breadth or the change in length dx. But L dx is actually the change in area, so work done is equal to gamma dA. An interface is a region between two immiscible liquids. So we can then think of interfacial tension, whereas we have initially been talking about surface tension. Even in this, there is imbalance in intermolecular forces at the interface. So we can talk of there being an interfacial tension as opposed to the surface tension we talked of earlier. This is usually lower than surface tension. Examples of values of surface tension gamma for some liquids is given in table 4.1. Show, page 65. This is in the 4th edition. Where does surface tension come from? Usually from short-range forces, which include van der Waals forces, particularly London dispersion forces, and hydrogen bonding. This is in alcohols, acids, ammonia, and in water. These forces are assumed to be additive. For example, let us look at water with surface tension gamma. This is the sum of the dispersion forces, contribution, gamma WD, and hydrogen bonding contribution, gamma WH. So the sum gives the surface tension for water, gamma W, is therefore equal to gamma WD plus gamma WH. Let us look at a different liquid, that is mercury. Here, the surface tension of mercury Hg, gamma Hg, is equal to gamma Hg dispersion, D, plus gamma Hg metallic bonding, M. Gamma HgM, this is the contribution from metallic bonding system. When we look at hydrocarbons, the contributions are entirely dispersion forces. Now let us look at phenomena at curved interfaces. Now at curved interfaces, when you have a convex interface, beta, and the other side alpha, it is found that the pressure in the vapor phase, beta, PV, is actually less than PL. This is because PL, that is in alpha, has an extra force from surface tension. If we look at a concave interface, that's the one in blue, we have beta in the vapor phase and alpha in the liquid phase. In this case, PV in the vapor phase is greater than PL. Again, it's because PV has got a contribution from surface tension. When the interface is flat, alpha and beta have equal pressure. That's PV is equal to PL. So the difference is due to surface tension. The angular flux equation gives the pressure difference. That's delta P is equal to gamma into second bracket 1 over R1 bracket plus 1 over R2 in bracket with the major bracket out. For a sphere, R1 is equal to R2 is equal to R. So the Laplace equation becomes delta P is equal to 2 gamma over R. As a consequence, a small air bubble has higher pressure inside than a big one.